Hi guys. Today the main topic is the beat tree. This is part two. So part one is I already took the video of it. So let's just recall what we just talked about. What is the beat tree? Um, to understand the beat tree, you have to understand why we are using the beat tree or those kind of thing. So actually, the beat tree is kind of advanced version of the binary tree. So it's like kind of this. The binary tree and the B tree, and there's more, the B plus tree or those kind of thing. So to understand this kind of B plus tree, you have to learn about the B tree. To understand B tree, we have to understand binary tree. So this is kind of really complicated, but I guarantee that if you just understand the core concept and also this is really being used in a lot of industry, so I think you're able to learn about, or like you're able to like learn this quickly than the others. So and this kind of B tree and B plus tree is basically used in the database indexing algorithm. So let's start with the array first and the binary tree and the B tree. I just already talked about this kind of last video, but let's just recap this. Let's say you want to insert um, this bunch of array, and but not this one. Sorry. Let's just being like practical. You like Pokemon. I like Pokemon too. Let's say you want to store. Let's say you are kind of like the tech manager, or you're like the head of tech in the Pokemon industry or Pokemon company, and you just find out that you wanna have to store the Pokemon data because you have to really make your data to store in some kind of database, because you can just pull it out and filter it, right? Because when you're trying to make a game, you have to make some kind of data, or example like version X and version Y. There's a the Pokemon that is gonna be used in version X, version Y, and Pokemon Black and White, or those kind of things. So you have to make it as a data. So how do we really make this kind of data? Let's say there's a Pokemon. I forgot the Pikachu. I don't know how to spell it. Pikachu. But whatever. So there's a Pikachu, and there's gonna be name, which is Pikachu, and there's gonna be gender of it, the male. It could be also female. And also, what else? The height. Yeah, but height like how many height like 65 centimeter, whatever. So those kind of thing is kind of this Pikachu we have. This not on the Pikachu. Every the Pokemon should have this kind of unit of the data, and this is called the record. I just talked about this in the last video, but let's just recap it. This is called the record, and in the thing, the important thing about this is record has to be have the key of it. So what do you mean the key? The key is the just the identifier to distinguish the which is who of this Pokemon. Because example, there's a duplicate of it, but also there should be some kind of unique representation of this kind of the data. So we commonly use ID value for the key of it. So this is record, and this is the key. Great. So, and now you have like bunch of Pokemon. Example, Charizard. There's a kind of like, of course you really have different ID like 100 or whatever. So let's say there's a bunch of the bunch of Pokemon. I don't know there's so many, how many of the Pokemon is in that word. So but let's say like 200 more. Let's say just 200,000. So, and that's really nice. We have a different data and we have lots of Pokemons. But there's a problem that we face. Like if you wanna find the ID 200, which is Charizard, right? But which means that we have to really like go inside this kind of record box. We have to like find the ID, and now even we find the ID, we have to like differentiate this ID is 200 or not. So that's kind of really kind of tedious. Example, but that process is really kind of kind of like a little bit complicated. Also, that has to be it's and that system and that process has to be even it has to be not in the ones. For example, you have a Pikachu which is ID 0, but if it's like 100, you're gonna do the same thing. But so we, the software engineer, great software engineer, find out that that's kind of tedious. So why don't we collect all of the keys in the record and put into one file? So that is called the index file. And also, but that's pretty nice. But so rather than making a record, like traversing this kind of unnecessary record, we just make it like this. Just a set of ID. That's pretty nice, but let's say your ID is like 100,000. That means that you have to really traverse to find out 100,000. And that's kind of really bad because that means that you have to really search for the every element for you encounter 100,000, which is caused like this. Let me try to explain with the graph. So this is the graph here, and it's gonna like look like this. So more you have n, the more your time complexity will increase. Like this. But what if we wanna or we can reduce this kind of time cost? So this is why the binary tree and the B tree and those kind of thing comes up. This actually R8 is that the time complexity ON. We really have to traverse like bot 0 to top to encounter 100,000, even though we don't have to do it. So binary, let's say we're just gonna use binary tree. 1, 2, 3, 4, 5, 6, 7. So binary tree is really simple. You have a bunch of array the elements to insert, and the node or the element has to be inserted go left of the tree if the int is smaller. For example, you inserted 1. Nice. You have to insert 2 and you go here. You have to insert 3 and you go here. And you have to insert 4 and you go here. But those kind of things. But since this is kind of really unnecessary, we can just make this binary tree into like really tree form. This is not really tree, just like array like. So we can just put it like this: 2, 1, 3, here, and 4, and 5, and we can just make it as a balance like 3, 2, 1, 4, 5, 6. But even though there's kind of unbalanced, we can just make it into like this: 4, 3, 2, 3, 2, 1, and 5, 6, 7. We can just put it like this: 5, 6, 7, and 8. So whatever. But even though we're trying to make it balance, like even though we put here 4 and we put like 5 here, and let's just say we put like 6 here. Even though we're trying to make it balance, you will learn that there's something not missing here. So let's say you wanna find you want to search the value, which is 5. You have to traverse this kind of nodes, right? So rather than the array, you don't have to really traverse this part. So that's really great. But even though you don't have to traverse this part, but when the binary tree seems like this, it just seems like array. So the time complexity is really same as array, the worst case. But the average case is O log n. But since there's the worst case, we were trying to find some kind of best algorithm to solve this issue. This is because our computer science software industry it is kind of really like this. What I believe is, okay, there's a problem, and if it's like repeated, and we can just replace it, we can just like simple form or advanced form, we just somehow made it. So B tree, there's also some kind of limitation of the binary tree, and also the problem of using binary tree, and so we make the B tree, and even though there's a problem of the B tree, we make the B plus tree. So let's say the B tree, the making B tree is really simple. We just have to decide the minimum degree amount. Let's say we just make it 2. So I'm just gonna try to explain after building B tree why this is kind of important. So let's say we want to insert the same value like here. So to get the max size of the node can handle, you can just simply use this formula. So this is equal to the 3. So our node can handle 3 keys. So let's put 1 and 2 and 3. And next our value is 4. We have to insert 4, but if we try to insert 4, the node is already full, right? So we have to make this make some kind of elements to go to the root and the child go to the left or right. But how do we really choose this some kind of the key is the one who being promoted? There's always a formula of it, which is t minus 1. Our t is 2, so it is actually 1. 0, 1, 2, 3. So this 2 is gonna be the parent key. Sorry, let's just stop for the moment and let's look at the formula of here. So if you look at the kind of like interesting the math, you're able to see some kind of like repeated thing. Even though we put some kind of add value or odd value, even value or odd value, example, we put 3, the answer is always the odd. Even though you put 3, it is 5. Even though we put 100, it's already 199. But I'm just gonna currently give you some kind of like interesting thing. If some kind of element is elements, and the length of the elements is odd, that means that you don't have to recalculate for the middle key. So this kind of formula actually for finding the middle key. Let's say you're the insert the, let's say 3, and 3 times 2 is 6, and minus 1 is 5, right? The value is odd. Let's say there's a 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And our t minus 1 is actually middle key. But like example, 3 minus 1 is 2. So even though we don't have to we don't really have to calculate those kind of finding middle key, we can just use the formula to get which is 1 is the middle key or primary key to be your parent. So let's go to the making parent. So this 2 has to be parent. So what we have to do is making 2 as like this part. So put 1 here and put 3 or 4. Yeah, this is right. So if you look at this kind of tree structure, unlike the binary tree, the bit tree is we always have the balanced tree. There is no some kind of like zero children, and also these kind of node can have multiple kids that you can also make this tree but shorter but longer for the search. Let's just begin. Now our element is to insert is 5. You go here because this is kind of extended version of the binary tree. 5 is bigger than 2. Okay, you insert into here. So let's say you insert 6. Of course, this is already full because the max keys was the 3. So we're trying to do the same thing. We make 5 as a parent, so we put it like here, and we make also the balanced tree. And let's insert 7 and 8. Like this. So this is also great, but also the problem is that this kind of really easy, but the thing is getting complicated when you insert the more value of it. Also when the root or the parent is gonna be full. For example, you insert 9. And you reach the 12. 9, 10, 11, 12. So it is already full. We have to make 11 as a parent key. When you're trying to insert 11 as a parent key, wait, hold on. Yes, like this. 9, 10, 11. Like this part here, like. So this is already full, and you just have to make this do the same thing. The 8 is primary key here. So you just make this as a parent. Like it's just already doing the same thing. But we really have to care about those kind of pointer here. So yes, we put 8 as a parent. We put like this. And when we try to get rid of it, and you just have to follow this 5 here. So 11 is gonna be here, and 12 is gonna be here. So this is actually the balanced tree. So there's no O and worst case in the B tree. The worst case is O log the T N, and O. The worst case also the same as this. If we have like some kind of like difficulty of understanding O log thing is, let me just try to explain more about this kind of mathematics stuff. It's really easy. Log, if you say like T is 2 and N is 8, the answer is 3. The reason why it is 3 because 2, I don't know what to say. 2 square 3 is actually the 8. This also represent the thing is that when you increase this kind of value, it's getting more smaller. For example, you put 4 here or 8 here, it's gonna be 1. So more the T increases, the value you will get is more smaller. Since we just put this T is 2, right? So our formula is the max the node can handle is 2 times T minus 1, which is the 3, right? But what if we make it 100? If the T is 100, the max keys we can have is 199. So that means that we don't have to really search for that. This is already really big faster because it has the more keys than this part. So more you increase the T, more you receive the lower value, which is you have lower value means that there's more time complexity with it. So this is kind of recap of the last video. So next video I'm just talk about why is it B plus T or why do we have to learn it, and also why do we make this kind of B tree as a faster? Why not the binary tree? Even I know readers are gonna use ON, but why do we really have to matter? Like ON is kind of really fine than other thing, right? So why do we have to care about those kind of the performance of the searching? So this is Have a nice day. See you next time. Bye bye.